Going into detail here, I want to give you the top few lines of evidence that the Big Bang Theory is not just an idea. It's what fits with what we actually see out in the universe. And then after we do that, we'll talk about the process of the Big Bang and the theory in detail. Music and applause. 059. Now, first off, we have something called Hubble's law. So when telescopes got big enough to actually look out into the universe and observe galaxies far away from our own galaxy, we can figure out by looking at the light which way the galaxy is moving. And it turns out that no matter what direction you look, that way, or in the southern hemisphere in a totally different direction in the sky, all of the galaxies are basically moving away. And not only are they moving away from our galaxy, the rate or the speed at which they're moving away is related to how far away they are from us. So if you wind the clock backward, then you come to an inescapable conclusion that all of these galaxies at one point in the past must have been right on top of each other. So that's an observable thing that we can see that kind of goes in line with the idea of the Big Bang, which is an origin where everything was very hot and dense and then some sort of rapid expansion event happened. You can think of it as sort of an explosion if you want to, that created the universe. Now that by itself is already a pretty mind-blowing idea, that everything is moving away from us and there must have been some origin point where everything was in the distant past. But not only that, when we began to build microwave antennas and start to look at the sky, not in the visible light that you see with your eyes, but with microwaves, what we find even today is that when you look at any direction in the sky, up, down, left, right, southern hemisphere, northern hemisphere, you see a very constant cosmic microwave background radiation in all directions. And it turns out that when you wind back the clock and go through the math that describes the Big Bang Theory, it must have been a hot, dense point and then some sort of rapid expansion or explosion. When you go through the math and see as time and space expands after the Big Bang, the hot radiation that was there at the beginning would be stretched out and cooled off. And after the age of the universe, that we have calculated to be the currently accepted age of the universe, that hot radiation must have then cooled off. And guess what? The calculated frequencies that we get for that Big Bang energy as it has cooled off through expansion of the universe turns out to be right at a color temperature of about 2.7 Kelvin. In other words, we look around the sky and we see the afterglow of the Big Bang itself. Because no matter which way we look, we see the exact correct frequency of radiation that we calculate if everything started at a hot, dense point, exploded, and then all of that radiation cools off as the universe expands. Now, if that's not enough, the third most convincing line of evidence that the Big Bang Theory is something that agrees with observations is that again, it's not just an idea. It's a mathematical theory that predicts what the relative abundances must have been in the early universe for when hydrogen was created, the lightest element, and then when helium was created. Because remember, before the elements coalesced in the Big Bang model, it was just pure energy. And then when things cooled off, atoms actually then formed. And then much, much later, stars formed. So we look around the universe and we see X amount of hydrogen and X amount of helium in all of these ratios around the universe and lithium and other elements, and those ratios exactly agree with the calculations that you get when you go through the Big Bang model and use its predictive power to calculate those ratios. So big picture, the Big Bang model of the universe is not just an idea that people just made up one day. It agrees with what we see in the universe. There are many more lines of evidence than this, but the most compelling is that we see all of the galaxies racing away from us and at a certain rate that's proportional to their distance. And that we also see a uniform, constant microwave background radiation that has a frequency that exactly agrees with what we would see if a hot, dense explosion happened and then cooled off as the universe aged. And when we look around to the elements in the universe, we see the exact ratios of hydrogen and helium and lithium that we calculate using the Big Bang model of the universe. And if I do my job right, almost every single sentence should be literally a wow moment for all of us. I like to talk about exactly what the Big Bang is, what the common misconceptions are, what the nature of time is, and really fascinating to me, the so-called fine-tuning of our universe for life. And so today, in a nutshell, I'd like to walk you through a recipe, so to speak, as if you were running through a cookbook for a recipe for creating the universe from scratch. Starting from absolutely nothing and ending up with you, with me, with all of the planets, all of the stars, and everything in the entire universe. So, before we can actually start our universal cooking show to create a universe, we need to grasp just how small things can actually get. And I mean really, really, really small. Let's start with something that might seem tiny but is actually enormous by the standards of the Big Bang's singularity, and that is a proton. No matter how hard you try, no matter how long you sit and think about it, you will never be able to wrap your head around just how tiny a proton is. And I don't mean just you, I mean me as well. I want you to think about a dot of ink, like maybe the period at the end of a sentence printed in a book. So that's a minuscule little speck. You could probably fit about 500 billion protons inside that tiny dot. And that's more than the number of seconds in 500,000 years. But here's the thing, a proton is absolutely, positively, literally gigantic compared to where our story begins with the birth of the universe. So to start our universe, so to speak, we need to think even smaller than a proton. Take one of those impossibly tiny protons that we were just talking about and shrink it down to a billionth of its size. It's already incomprehensible, but when you shrink it down to a billionth of a size, it's totally beyond what I'm capable of visualizing. But give it a shot. Now, you're getting closer to the scale that we need. I want you to pack about an ounce of matter into that inconceivably tiny space, making the density of that dot totally and utterly incomprehensible. And we're ready to begin. But wait, we're getting ahead of ourselves just a little bit. Let's pause for just a second and talk about time for a moment. I know that all of us have pondered the concept of time at one point or another. When we discuss the Big Bang, people often ask what came before the Big Bang. So, it's a perfectly logical question, but it contains a hidden assumption that there was actually a before to begin with. You see, time itself began with the Big Bang. There was no before, because time didn't even exist until the Big Bang actually happened. So, I know what you're thinking. It's making your brain hurt already. That's part of talking about that stuff. It's bigger than any of us can really truly comprehend. Part of the reason this is so hard for us to visualize or think about is because we're all taught that there's this thing called space and it's everywhere, and all of the matter, like the Earth, the planets, the coffee cup, whatever, it's stuff inside of this scaffolding called space. And so we have been born and interacted with the world thinking of space as this thing that just exists everywhere. And the same thing about time. You become aware of time when you're a little child and you learn how to tell time, and so it's this thing that's just always going on in the background. Now along comes Einstein later, and through the theory of relativity, we now know that time is not a concept that is just independent of everything else. Time can tick at different rates depending on how you're moving, depending on how much gravity is around. That is a fact. We know it's a fact because we can build devices like atomic clocks and such that depend on that, on understanding that, to actually function. But also, space is actually not a rigid thing either. It can change. Depending on gravity, it can warp space and time and your state of motion and other things as well. But still, even though you might know that, it's really hard for us to shake the concept that time and space are not always everywhere. But you have to try to use your imagination. Right at the Big Bang, if the Big Bang actually happened according to the way the theory is set up, and I presented several lines of evidence which was not exhaustive that it agrees with observational things that we see in the universe around us. But if the Big Bang happens according to the existing theory, that before the Big Bang there was no time at all. There was nothing ticking. Right? There was no change in entropy or anything like that going on before the Big Bang. There was also no space. Right? Now, it's not totally true that we understand everything at that exact moment of the singularity. So, we don't know if time, didn't exist at all or if it manifested in some totally different manifestation that has no relevance or nothing that we've seen before. But the concept of time that we think of as this ticking that just keeps going on and that governs how things change, how things break down, basically the increase of entropy, that thing did not exist before the Big Bang. So asking what happened before the Big Bang or what was present before the Big Bang, it literally makes no sense at all. I want you to think about it this way. Asking what came before the Big Bang is kind of like asking what is north of the North Pole. The question itself doesn't make any sense if you've run out of north. In other words, if you go all the way to the North Pole and then you ask yourself, well, what is north of the North Pole? In any direction you go, if you're standing on the North Pole, then, there is no north of that, because if you deviate from north, then you've already gotten to the maximally north position. And if you go in any direction, you'd have to turn around and go north again. So asking yourself what is north of the North Pole is a nonsensical question. Asking what happened before the Big Bang or what the universe, that what space and time looked like before the Big Bang makes no sense because it did not exist before the Big Bang. Here's another analogy I've never heard anybody else use. So, I'll just tell you and you can decide to discard it or embrace it. Think about a pot of water that you put on the stove and you add heat to the bottom, like a flame from a stove, and it's boiling, right? But before it boils, it's just really, really hot, but it hasn't actually reached a boil yet. If you look down in the bottom of the pot, right before it starts to boil, you will probably see some bubbles, on the bottom of the pan that are sticking to the bottom of the pan. They begin to form as these little bubbles all over the bottom of the pan. And as you add more heat, or if you just hit the side of the pan, they'll be dislodged and they'll float up. And eventually with more and more heat, you reach a rolling boil. But I want you to think about those little bubbles which have formed on the bottom of the pan as I'm adding heat. You can think of those little bitty bubbles as almost like a Big Bang just about to happen, right? The singularity, so to speak. It's not a great analogy because the singularity is different, but it's something that is there and before you added the heat, it wasn't there at all. And then as you added more heat, it dislodged from the bottom, rapidly expanded, and then rose up to the top. You can think of that as like the expansion of the universe, sort of. So a lot of scientists think about the Big Bang as being kind of like a phase change. So the analogy I'm giving you is not too far off. I mean, obviously it's not right, but if I were to ask you if, one of those bubbles was a universe, and by the way, if there's a bubble right next door, maybe that's an adjacent universe totally and independently separated from the first universe. So, you could have two universes right next to each other, like the multiverse idea. Okay. But if I were to ask you at the moment that bubble was there, ready to pop off, and I were to ask somebody living in there, what was this place like? What existed before the Big Bang? And then they would say, well, there was no before. Why? Because before I added the heat, there was no bubble at all. There was no agitation. There was no Big Bang. There was nothing. The concept inside of that bubble of that universe existing did not appear in that region at all until the Big Bang, event, whatever it was, happened. And so just think about that. And so this is a little bit philosophical, but the idea of space and time did not even come into being until the Big Bang actually happened. So you can think about the Big Bang as the moment the stopwatch started moving. I want you to think about what happened when that watch, so to speak, started ticking. Now, in the first fraction of a second in the Big Bang model, and I'm talking about time frames so short that they make a lightning bolt look like it's moving through molasses. In other words, really short intervals in time, something really extraordinary happened. According to the Big Bang model, the universe underwent what we call cosmic inflation. Basically, most people think that the Big Bang is just something that boom, explosion, and happens. Well, actually, it's a lot more nuanced than that to get the theory to match what we actually see in everyday life. So, in the earliest stages, the first few fractions of a second, it underwent rapid inflation. And this is where Alan Goose's inflation theory comes in. In 1979, Goose proposed that in the first 10 to the minus 34 seconds, that's an incomprehensible fraction of a second, 10 to the minus 34 seconds is a decimal point followed by 33 zeros and then a 1, the universe underwent an expansion that would make a rocket ship look like it's standing totally still. The universe doubled in size every 10 to the minus 37 seconds. Basically, it was this incredibly fast inflationary period. Impossible for us to truly comprehend, 10 to the minus 37 seconds, the universe doubling at that rate in that interval. And after the inflationary period happened, everything slowed down, continued to expand but slowed down compared to the original inflationary period. Now, this inflationary model of the Big Bang primarily addressed what we call the horizon problem and the flatness problem with the original Big Bang theory. Remember, theories are revised when they don't explain observations. So in this case, the universe appears remarkably uniform across super vast distances despite not having enough time to reach what we call thermal equilibrium according to the standard or original Big Bang model. So the inflationary period rapidly expanded the universe, smoothing out any initial regions or irregularities and explaining this uniformity. Basically, the original Big Bang theory was proposed and then people start studying it and they say, well, if this is true, then it doesn't really fit with this piece of data. If this is true, then it doesn't really fit with that piece of data. And instead of throwing away the theory, what people do is they make modifications to it and say, well, maybe it was not a uniform expansion. Maybe there was a super rapid period of expansion in the beginning, which then slowed down a little bit, right? And that was called the horizon problem. Basically, when you look at different regions of the universe, super far apart, they appear very, very uniform. They need to be in contact with each other long enough so that everything can be smoothed out. And then after the expansion happens, we get to the uniformity that we actually see in the sky today. And the inflation problem addresses that. Also, in the original Big Bang theory, before inflationary theory was presented, the universe's geometry was calculated to be a curved geometry. Now, what I mean by that is space and time are curved in their relation to each other across the universe. Think of a flat sheet of paper being a flat geometry, but a curved balloon being a curved geometry. Now, it's hard for us to visualize the three-dimensional curvature instead of a two-dimensional curvature. And also, time is curved in there as well, which means the ticking rate can change as you move around the universe as well, but the concept is the same. Visualize a curved sheet of paper or something bent. So, the original theory predicted a bent or a curved model of the universe. But actually observations that we were able to then do, showed when we measure different parts of the sky that the actual, flatness of the universe is pretty darn flat. It's not very curved at all. And so that was solved or at least explained by the inflationary model of the Big Bang theory. So what was actually happening during this explosive growth? So this is where the four fundamental forces of nature come into play. So today we know of four distinct forces. Any force that you've ever experienced has been categorized as one of these four. The first one, which is the weakest one, is all called gravity, and that keeps the planets orbiting the stars and, you plant it on the ground and all that stuff. Then you have electromagnetism, which holds atoms together and also gives us light because photons are related to electromagnetism. Then we have the strong nuclear force, which binds the atomic nuclei together into atoms. And then we have the weak nuclear force, which helps to govern radioactive decay processes. Four fundamental forces of nature. Now, here's one small caveat. Gravity is by far the weakest of these forces. Even though we kind of think of it as really strong, it's millions of times weaker than any of the others. The question is it a real force? So, Einstein really showed us that gravity is not a true force. It is just a result of the curvature of spacetime. It's a geometric thing. Now, in modern particle theory, there is actually a particle that carries the gravitational force, which we call a graviton. And physicists are still wrestling with trying to bring those two ideas together. We still refer to it as a force, even though Einstein says it's more of a geometric thing and not a true force. Particle theory says, yeah, it's a force mediated by something called a graviton, but we've never discovered a graviton as of yet. Just know that some of these ideas are still being worked on. Now, back during the early expansion of the universe, it's really fascinating because in the heat and density of the early universe, which are incomprehensible, these forces, these four forces of nature, were calculated or predicted to not be separate at all. The Big Bang theory predicts that at that point they were unified into a single superforce, so to speak. And as the universe expanded and cooled, these forces separated out, kind of like water freezing into ice or vapor condensing into liquid water. Sort of like a phase change for the forces in the universe. So gravity is predicted according to the model to have split off first, becoming the weakest but far more reaching across the universe as the force that we see today that holds galaxies and stars together. Obviously, the holy grail of science is really trying to unify all four of these forces. We see distinct forces: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. And the theory goes is that maybe those are just different aspects of a single superforce. And that when the universe was much smaller and much hotter in the early stages of the Big Bang, there was really only one force. And as everything expanded and cooled, these four forces kind of coalesced or, kind of like phase changed, for lack of a better word, into the distinct forces that we see today. So people study the Big Bang, where the forces are predicted to have been unified, to get clues into unifying the four forces. Now why do people care about a grand unified theory anyway and unifying all of these forces? Well, because if we understand how the forces are cross-linked and how they are related to each other, then we can understand how to manipulate matter and energy, generate power, build spaceships, pretty much any machine that we have can be built better if we understand the fundamental forces of the universe. So, back to the Big Bang expansion. In the first microsecond, the universe was so hot that matter as we know it could not exist at all back then. Instead, it was really just a cosmic soup of quarks and leptons. These are the most fundamental particles that we know of, which are even more fundamental than the atoms that you know about on the periodic table. It wasn't until about 3 minutes after the Big Bang that the first atomic nuclei could even form at all, mainly hydrogen and helium with a tiny dash of the third element, lithium, thrown in. But here's where we hit a puzzle that's been bothering scientists for literally decades. The Big Bang theory predicts that only the lightest elements were created during the initial actual Big Bang expansion. In other words, hydrogen, helium, and a trace of lithium is predicted to be the only elements to have actually been created during the actual initial Big Bang. And these are the first 3 elements on the periodic table. But as you know, there's like 100 more elements after that that we already know exist. So, where did they come from if they didn't come from the Big Bang? I mean, look around you. Your body contains carbon, right? And nitrogen, oxygen. You're breathing it all the time. Dozens of other elements, your car, your smartphones, they contain metals that are much, much heavier, the silicon, transistors and other things that are inside of the microprocessors that you use every day. And if they were not made in the Big Bang itself, where did they come from? Now, the answer quite literally comes from the stars. Now, it's kind of mind-blowing, but every atom of carbon in your body, every oxygen molecule you breathe, every iron atom in your blood, these were all forged in the hearts of dying stars billions of years after the Big Bang. Now, when massive stars explode as supernova, for instance, they scatter these elements across space. So really, we are quite literally made of stardust. I want you to really sit and think about this. Only hydrogen and helium and a tiny bit of lithium was actually created, according to the Big Bang model, in the actual Big Bang itself. Right? And so what happens is for a long, long time these elements are attracted gravitationally and they get clumped together. And then eventually when gravity pulls them together and they get big enough, the pressure inside gets so hot and so much pressure that they get fused together into heavier and heavier elements. But when you go through the theory of nucleosynthesis, right, and fusion theory, we know that you really can only get elements up to about iron from nuclear fusion in stars. So you know, the nitrogen and all of these others that we talk about, the oxygen, they were created in the original stars that are long gone. Because what happens is when a star runs out of fuel, then the pressure inside goes down and then it goes into a very unstable period, and very often, depending on its mass, it can explode in a supernova. So the fusion process creates elements up to iron, but actually anything after iron is not made in normal fusion reaction in any star. The only way you get anything after iron is when a star actually explodes. So lots and lots of things that you use every day and smartphones and things have heavier elements than iron, right? All kinds of things. And so all of those must have come from ancient stars that actually exhausted their fuel, exploded, and they formed the heavier elements, which then later coalesced onto our planet to make, the heavier elements that we mine out of the ground and use for various things. So, think about that. You literally are made of atoms that were inside of stars. Now, I touched on it in the beginning because I wanted to get it out of the way in the very beginning, but I want to dive into the evidence for all of these ideas a little bit more. How do we know actually that any of this stuff is actually true? I mean, honestly, it sounds totally absurd that everything started from an infinitesimal speck exploding and then creating time and space as it expands. So, I want to talk about one of the most remarkable discoveries in the history of science. I touched on it earlier. I want to talk about it in a little more detail, and that is the cosmic microwave background radiation. I personally think that this should be taught to every kid in science class in about 4th grade. This is literally the afterglow of the Big Bang explosion itself. And it was first discovered by accident, total accident, in 1964 by Arno Penzias and Robert Wilson. So these two fellas were working at what's called Bell Labs with a sensitive radio antenna. And they kept picking up this persistent background noise, quite literally static in what they were receiving. And so they were confused. Why is there static in this thing? They checked everything. They actually went and cleaned out the pigeon droppings which were on their antenna, and they referred to in their, scientific papers as white dielectric material. It was bird poop. And they checked all of their equipment. But the noise, no matter what they did, would never go away. There was always this background static at a certain frequency. And they did a lot more than this. They actually pointed their antenna at different areas of the sky. They checked it at different times of the year. They tried, disassembling, reassembling everything. And no matter what they did, no matter where they pointed it, at this certain frequency they always picked up this background static at a certain frequency in the sky. So what they stumbled upon was the oldest light in the universe. So when the universe was only about 380,000 years old, it cooled enough for electrons to combine with protons, and those formed neutral hydrogen. Suddenly, light could travel freely throughout space. And that light has been traveling ever since, stretched by the expanding universe until it reached us today as microwave radiation. Now, you might say, if you're paying attention, well, wait a minute. You said the first atoms formed a few minutes after the Big Bang, and now you're telling us that the microwave background radiation, came from electrons recombining and forming atoms like 300 and something thousand years after the Big Bang. Well, here's what's really going on. In the first few minutes after the Big Bang, the electrons and the protons could very briefly recombine and form the very first atoms. But everything was so hot that those atoms were not truly stable. So we say that those first atoms kind of formed then, but they were, think about a plasma, a soup of charged ions. I mean, they can recombine and then immediately be broken apart again because it's so hot. Something else smashes into it and disrupts it. So the first atoms of hydrogen were formed after the first few minutes. But we really say that the first elements of hydrogen that could actually be stable in bulk without immediately breaking down again into, electrons and protons, those didn't happen until much later when the universe cooled off, about 300 and some change thousand years after the Big Bang. And much like what happens in a laser or even in a regular light bulb, photons are emitted when an electron comes out from, far away from the atom and drops in and goes into a stable orbit around a nucleus. And so whenever, that was done, it releases a photon of a known energy. And by the way, we know that the universe is expanding. According to the Big Bang Theory, and as the universe expands, that energy that's in there, the photons that were literally created at the moment of the Big Bang, we know what their frequency should have been back then, their energy levels. And so as the universe expands, it stretches the wavelength out because it's not just that the atoms or the energy are exploding inside of space. You got to remember, space itself is getting stretched out and kind of being formed as the explosion happens, so to speak. And so what's happening is the energy that was there during the Big Bang, the photons, their wavelength is being stretched out. And so we know by looking at the sky what the wavelength of the energy that we see is up there now. And by going and winding the clock backward, we know that that energy is coming from the Big Bang because we know the energy of the photons, the wavelength and the frequency that must have been emitted when the first atoms formed. And so then if that was stretched out over the given age of the universe that we have calculated, we should get exactly the frequency of the microwave background that we can look up and see everywhere. So when we look up and see that, we're looking at the energy that was first released at the Big Bang. So not only do we look everywhere and see the exact correct frequency uniform in all directions that we would calculate if the universe, came to being exactly as we talked about there, but there's a precise pattern when you look at that, sky because the sky has been mapped and we've measured the microwave background very accurately over the years with satellites. And there's temperature variations in that radiation that observe that matches the observations and the theoretical predictions with remarkable accuracy. It's like finding a fingerprint or something at a crime scene that matches perfectly our suspect. So it's not just like one number over there. It's the precise variation across the sky matches exactly what we would have calculated. Now, as I mentioned before, we have what's called the abundance of the light elements in the universe. So, the Big Bang Theory predicts that in the first few minutes, the universe should have created a very specific amount of hydrogen that can be calculated according to the Big Bang model. A very precise amount of helium, a very precise amount of lithium according to the model. And when we look at the oldest, most pristine parts of the universe in the sky, what do we actually find? Exactly these proportions. It's about 75% hydrogen, about 25% helium, and a tiny trace of lithium. It's kind of like discovering that the recipe card matches perfectly with a cake that you randomly find somewhere in a store. And thirdly, as I mentioned before, there's expansion of the universe first discovered by Edwin Hubble. We actually named the expansion after Edwin Hubble. Every distant galaxy we look at is actually moving away from us. And the farther away that it is from the Earth, which we can measure, the faster it is moving away from us. If you run this cosmic expansion backwards, like rewinding a video or something, everything converges to a single point in the past. And remember, it's time and space that's actually being shrunk down as well because that was created during the expansion. And this observation was actually made before we had all of the other evidence, and it was the first big hint that led to the Big Bang Theory in the first place. The fourth line of evidence for the Big Bang, which is honestly really striking, is what we call the perfect sky problem. Look at any direction in space, and the temperature of the cosmic microwave background radiation is almost exactly the same in any direction that you point your instrument at. It's varying only by about 1 part in 100,000. Now, this uniformity was a mystery until cosmic inflation theory came along. And when you run the calculations, the inflation theory explains how the regions of space that could have never communicated with each other because they're so far apart in the sky today, they were somehow on top of each other, intermingled, when the inflation period happened at the same temperature. And it's like finding out that sort of like two people on opposite sides of the Earth, somehow wrote exactly the same story without ever actually interacting. But then you figure out that, they were in the same place, in 1900 or something, and that's where they chatted about the stories that they were going to write. So these 4 pieces of evidence, and there actually are others as well, but these 4 taken together form an incredibly strong case for the Big Bang Theory. Each one independently, because their independent measurements, points to the same conclusion. And unlike many other scientific theories, the Big Bang makes very specific predictions that we can actually test and that we actually have tested, predictions that have been confirmed again and again by actual observations. But perhaps the most compelling aspect of all of this stuff is that no other theory has been able to explain all of these observations simultaneously in the same framework for a same alternative theory. And so alternative theories might explain one or two pieces of evidence, but they fall apart when trying to explain everything we see and the totality of everything that we measure when we actually look at the sky. And so the Big Bang Theory not only explains what we observe, but it explains what we have predicted, several of these phenomena before we actually had the technology to observe them. So in other words, we have in many cases predicted what should happen before we even had the instruments, and then later the instruments were invented, pointed at the sky 10 years happened to measure these things like the galaxy recession or something like this, and then, oh, it matches exactly what the calculation said. So let's talk about the age of the actual universe. Based on multiple lines of evidence including the cosmic microwave background that we talked about so much, the rate of expansion of the galaxies that we can measure, and the ages of the oldest stars that we can also measure, we now know that the universe is about 13.8 billion years old. But what does that number actually really mean? Now, I can't speak for you, but you know, I think I can visualize 100 years. So it's about a human lifetime, roughly. 1,000 years I can kind of visualize it because that's like, you know, roughly, 10 human lifetimes, maybe a little bit more. Okay. You start getting into hundreds of thousands of years, and it starts to get difficult for me. You get to 1,000,000 years, I kind of comprehend it because it's a nice multiple of 1,000, but it's basically hard for me to figure out. You get to 200, 300 million years, and then you get into billions. Then suddenly, my conception of what it is stops and basically it just becomes a really big number. It's basically impossible for us to understand how long that is. But it's long enough for multiple sets of stars to have coalesced, exhausted their fuel, exploded, made heavy elements, and coalesced again into other planetary bodies and stars. Let's try an alternative way to visualize how old that is. If we actually compressed the entire history of the universe into a single year, with the Big Bang actually happening on January 1st, our solar system wouldn't even form until September. Think about that. September. Life on Earth would start in late September. Dinosaurs, which we think about as being so old, right? They would appear on December 25th of this year, and they would go extinct on December 30th of this year. And all of recorded human history, which we also think of as being pretty old, would take place in the last 14 seconds of December 31st. Now, stop and actually think about that for a second. If the Big Bang happens on January 1st, right, then all of human history, the rise and fall of Rome, the building of the pyramids, the invention of language and agriculture and math and all of the leaders and the wars and all that stuff in this, framework, it takes place, all of it, during the last 14 seconds of this year, with the Big Bang on January 1st. So, we have talked so much about how the universe began, but a question that's been asked for just as long is, how would the universe end, or will the universe actually end? Now, scientists used to actually think that there were three main possible fates for our universe when it ends. So, the first one is it could expand for a while until gravity causes it to collapse, slow down, and collapse back in on itself. Or it could expand forever, just getting bigger and bigger and bigger. Or it could be perfectly balanced somewhere in the middle where it kind of just slows down and kind of peters out. Now, we know thanks to observations of distant supernova and also the microwave background radiation detailed studies that the universe is not only expanding, but it's actually accelerating in its expansion. Now, if I could do a record scratch, it would be record scratch right now. Nobody should ever expect this to happen. You've got this exploding thing. You would think gravity would slow it down and maybe pull it back in, or maybe it would expand forever or whatever. You would never ever guess that it would be accelerating. How in the heck is that possible? But that's what we find. They did multi-year studies of, which can only have been done very recently, by the way, with modern instruments and modern computers. And we see that not only is everything moving away from us, which is what I told you from the beginning of the video, but everything is accelerating away from us, going away faster and faster and faster over time. Now, the currently accepted idea, which is just an idea and a theory, is that this acceleration is driven by something we